All right, so today looking at composition of functions, which basically means take two formulas. Let's say you got to get one answer from one formula, and the answer from that formula you want to plug into a different formula, right? Basically, you'd have to do two formulas every single time. Well, there's a way to take two formulas and make them into just one, so you don't have to plug into one formula instead of both. That will do both of the different things it needs to do. So that's what we call composition of functions or formulas, right? Just combining multiple functions or multiple formulas into a single thing, right? So there's a few constrictions or whatever, but otherwise it's pretty straightforward algebraically. So one of them is that the first formula you have has to be included in the domain that you're plugging into, meaning if you get an answer on a certain formula that's negative, well, you can't plug that into a square root function, right? Because square roots can't do negative. So anything that you're using in one function has to be inputable into the second function, which we'll get into what that looks like a little bit later. Okay, and we have different notation here, and these two right here are equivalent to each other, so they're both read f of g of x, f of g of x. And they're read the same, so whether it has this open dot or if it's written like this, I mean the exact same thing. Okay. So let's just get into calculating, and the first step is going to be the composing of the functions. The second is just going to be simplify using all the pre-algebra rules, algebra rules, whatever you know, to simplify it as much as possible. Okay, and that's the part that actually takes more time, not really the new part. So let's do two parts here. Okay. The first, let's find f of g of x. So what we're doing here is that normally we'd plug in a number for f of x and get an answer. This is saying, instead of plugging in a number in for f, I'm going to plug the entire expression of g of x in for each x. So here's g of x right here. It's 4 minus x. So in f, I'm going to substitute every single x, not with a number like we normally do. Like if this is f of 4, I just do 3 times 4 minus 5. Instead, I'm going to replace x with this entire function, 4 minus x. Okay. Nothing more than that. Okay. So I'll have 3, and the x, which is going to be 4 minus x. And then I have minus 5. And you have composed your functions. And simplify as much as possible, doing whatever algebra that you know to simplify. So we can distribute and combine like terms. Negative 3x, and that'd be 12 minus 5, which is 7. And if you wrote 7 minus 3x, that's fine too. All right. And now let's do the compose them the other way. So instead of plugging g into f, right, let's take every value of x and g and substitute in 3x minus 5. So this would be g of f of x. So I'm substituting in f of x for every value of x of g. This time, this x is replaced by 3x minus 5. There we go. And once again, simplify as much as possible. And we have negative 3x plus 9. So note that the one we just did, g of f of x, and the one we did first, f of g of x, are not equal to each other. So the order matters on how you plug things in. So it's like division. Do 1 divided by 2 and 2 divided by 1, two different answers. F of g of x, g of f of x, two different answers. Okay. Now, there are certain cases that they actually do come out the same, and that's how you know there's something called, they have a relationship called being inverses of each other. And we'll look at that a little bit later. So far, it's just algebraic, and they're non-commutative. Order doesn't matter. All right, so let's practice that using a quadratic, a rational, and a radical function. And really, if we just get the notation down, the algebra is going to be pretty familiar. On this one, since we're doing a rational, we're going to have some fractions, but nothing we can't handle. So f of g of x so that means I'm going to use f. I'm going to plug into the function of f. So each of these x's right here is going to be replaced with g of x. That's what this is. So I'm going to plug this in and replace it with each of those x's. So we have 1 plus x over x plus 2 squared minus 3 times 1 over x plus 2. It's just this very function, but each x replaced with the rational function. And then simplify this as much as possible using all the fraction properties that we know. So we can simplify both of these fractions. First one, I could just square the top and square the bottom. I'm not going to expand the bottom. I'm just going to write it as x plus 2 squared. So that simplifies that a little bit. The second one, I can multiply the tops together, 3 times 1. So it'll be minus 3 over x plus 2. And everybody's favorite, we got some fraction work to do. So of course, if we're adding subtracting fractions, you need to find common denominators. This is x plus 2 squared, 2 of them. This is x plus 2, only 1 of them. So we're going to multiply by another. This will make the denominators both x plus 2 squared, because now there's 2 of them. And of course, we have to do the same thing, top and bottom. So first doesn't change. Second simplifies. So we'll have minus 3x plus 6 over x plus 2 squared. Now the denominators are the same, and we can combine everything on the top. Now you got to be careful. You're actually subtracting 3x plus 6. Not just the 3x, meaning you have to think about it this way. So we can't just say minus 3x and then 1 plus 6 is 7. It's actually subtracting everything we see here. So minus 3x is minus 3x, and then 1 minus 6 is positive 5. There we go, a little small down here. X plus 2 squared. So a bunch of fraction work, but it's the same rules from the 5th grade, right? Just with polynomials, you don't overthink it. Don't do anything different than you normally do. It's really just remembering things like the parentheses, right? Nothing more than that. Don't overthink it. All right, let's go down to C and practice f of h of x. So we're going to have h, which is a radical, and we're going to plug that into right here. So each of these x's, instead of replaced by here, we're now going to replace it with square root of x. So notation first, write it out. F of h of x, lots of parentheses, it's going to be square root of x squared minus 3 times square root of x. And lucky for us, this one, much simpler to simplify. So x square root of x squared equals x. And then the second part, 3 times root x, is just 3 root x. We can't simplify anything. And that's it. That's all we can do here. Now, both of these also ask for domain. So we got to reach back to Unit 1 and remember all the domain rules. And recall that, well, we can't divide by 0. This would be a vertical asymptote. So it looks like x can just not equal -2. And usually with domain, it's easier to think about what it can't be and then get your answer. So if x can't be -2, and that's the only number it can't be, how do you write a statement that says everything but -2 is okay? So everything would be from -infinity to -2, and then everything from -2 to infinity, right? That's the same thing as saying just everything but -2. All the numbers except -2. And then for the radicals, what can x not be with square roots if we're not doing imaginaries? Yeah, so for here, it's different rules. So it's not necessarily that it's difficult, but you're going to have different rules for different functions. Rationals, it's all about dividing by 0, can't do it. With square roots, it's all about x cannot be negative. Right? So as long as you don't have a negative here, you're okay. So we can have anything from 0 to infinity. Should I include 0 or not? So is it a parenthesis or is it a bracket? Yeah, bracket. Because we can plug 0 in. Square root of 0 is 0, right? I'd get an answer of 0, but that's still an answer. It's not like I'm taking the square root of a negative. Okay? So, same old rules. All right, so let's look at B. Let's go back to here and look at B. Let's find g of f of x. So, this time we're plugging in f of x to g. So we know, yeah. So let's see what we get. So that means this g of x, I'm replacing this x with f of x, this whole thing. So just replace this single x with x squared minus 3x and plus 2. All right. So, what is the domain? Remember, the domain is about the denominator not being 0. So how can we figure out where this equals 0? What numbers when you plug in gives you a 0? And kind of hard to tell in this format. However, if you factor it, that's when you can see easily when it's equal to 0. So if it's not factored, you need to factor it to know where those zeros are. So they multiply to positive 2, they add to -3. Two numbers that multiply to positive 2 add to -3. And of course, you'll get -2 and -1. -2 minus 1, -3. -2 times -1, positive 2. And now we can see this is going to be equal to 0 at 2. So x cannot equal, switch. So x cannot equal 2, and from here cannot equal 1. That would make both either of these 0. Can't do that. So once again, cannot equal. So once again, we got to write a statement that says all the numbers work except these. Right? So everything from -infinity to, what should we put? 1 or 2? 1. And then what else? From 1 to 2. And then from 2 to infinity. Union? Yep. There you go. Now recall, since there's 2, why are there 3? And just in case you need to, right? So we have a vertical asymptote at 1, and again at 2. So that's why we have 3 answers here, because there's 3 different regions. 1, 2, and 3. So 2 vertical asymptotes make 3 different regions. That's why we have 3 answers in a domain. All right, lastly, let's do h of f of x. All right, so go back up here, h of f. So I'm going to plug into h. Right here, I'm going to take f, x squared minus 3x. I'm going to plug that in for this x right here. So we have h of f of x. Will be the square root of x squared minus 3x. Now we have to find out, where is this greater than or equal to 0? Right? We can't have a number where we plug in here that will give us a square root of a negative. So we have to figure out, well, where do I get negatives? For what values of x's do I get negatives? So I don't include them in the domain. Just like above, same thing. I had to do the same thing, and factoring was the key. So when you're trying to figure out domain, factoring is usually a good thing. So factor out a GCF of x. So from here, we know x can't be 0 or 3. Right? Well, actually, they can be 0, 3. But these are going to be critical points. I'll say this, the critical points are 0 and 3. Because if you plug in 0, you get 0 minus 0, square root of 0, 0. So x can equal 0. Same thing with 3. 9 minus 9, 0. Right? It's where you get a 0, but unlike denominators where you can't have zeros, square roots, okay. Okay to have 0. So what we want to do is, we have 3 regions once again. Just like we had 2 vertical asymptotes. So we had 3 different regions. We have the same thing here. We have 0 and 3. We just need to find out what values give you positive numbers, not negatives. So this is how we checked for critical values back in Unit 1. We wrote these out. We said, well, let's plug in something. -1, that's a little less than 0. Something between 0 and 3, let's say +1. And then something bigger than 4. Right? And we were looking for like increasing, decreasing, things like that. Well, now we're looking for, where is it positive, where is it negative? Negatives don't belong, positives do, because I can take square roots of positive numbers, but not negatives. So if I plug in -1, and you can use either one of these, either way. I'll use the top one. -1 squared is 1, minus 3 times -1, which will be plus 3. Right, so that gives me a positive number. If I plug in +1, 1 minus 3, -2, that gives me negative. So that means I don't want to include from 0 to 3 in the domain. So far, I have this, -infinity to 0. That's good. And then, same thing, plug in 4. 4 squared is 16. 16 minus 12, positive. So anything greater than 3 also works. And we've got the U. All right. Now here's the fun part. What's wrong with my answer? Where's the mistake? Brackets, just like over here, right? 0 is okay. So I started off earlier saying, oh yeah, if you plug in 0, you get square root of 0. So 0, okay, you can plug that in. Same thing with 3. Plug in 3, you get square root of 0. That's still part of the domain. There's no dividing by 0, so that's why they're included. So after domain, you saw this in Unit 1. After you do everything, you get all the numbers, you're calculating it, you always go back one more time and just look at parentheses and brackets and just make sure you didn't just, draw a line wrong. So it's small but important. All right, so that's the nitty-gritty stuff. You know, detail-oriented as usual. You have to be careful and double-check everything. Okay? And on your homework, there's also going to be absolute value functions and things like that, parabolas. Just remember, absolute value and parabola, you can have, the domain is all real numbers. Okay. Usually it's the rationals and the square roots where you have the restrictions. But you can plug any number into absolute value, and you can plug any number into a parabola, or, you know, quadratic or cubic, and with no problems. All right. Second part, let's do this, but without the expressions, and do it all graphically. So what if instead of having two expressions for f of x and g of x, you have two graphs? Right? So make this actually is a little bit easier. So f of g of x, f of g of 3. So plug it in properly. So we want to find out, well, what is g of 3 equal to? So look at the function of g over here, and g of 3 is right here, and that equals 1. So I'm going to replace g of 3 with 1. And now you have the second question. So what is f of 1? So you go to f, and you look to 1 right here, and you get an answer of 2. So a two-step process using both graphs for each one. And let's try one more over here. Let's go. This one, D. So what is f of 1? Yeah, hint. Oh, no, sorry. Negative 1. That's a negative. F of negative 1. Here's f. Here's negative 1. So way up here. So we get 6. And then on the bottom, we have f of, and what is g of 3? So you go down to g, find 3, get 1. So we have 6 over f of 1, back to here. F of 1 is, once again, 2. Same like it was right here. F of 1 was 2. So, and simplify. All right, try the rest of those. B, C, E, and F. See what you get. Check with one another as needed. Looks pretty good. Have all the work there and you'll have no problem. So let's continue on to the next part. So, as you've known in math, and I've mentioned this many times, that once you learn how to do something mathematically, there's going to come some point where you learn how to do it in reverse. The reversibility of math is a whole other, probably a problem that you want to know. And the same thing will be true in calculus. You learn a semester of differential calculus. That's the algebra A, or the calculus A, and then you have the integral calculus, which is just reversing everything. So if you already have a function that's combined, can you break it apart into two functions? That's the question. Of course you can. So the inside function here, we're going to call g of x. And the outside function will be the f of x. Now, a good way of looking at this is just think about parent functions. So looking at this is a parabola, right? So what's the parent function of a parabola? That's just x squared. And what are we plugging into x squared? The x plus 3. So that's just what makes it, if you're graphing this, it moves it 3 to the left. Right? This is a parabola that's moved 3 to the left from the parent function. So if you can identify the parent function, the composition, let's just call this, or decomposition of functions, right, is pretty straightforward. So what is the parent function of 1 over x minus 5? That's just the rational function, just 1 over x. Okay. Start there, and then we're going to substitute in x minus 5, which makes it move 5 to the right on the graph. And parent function of square root of x plus 2, it's just the square root of x. And of course, we'll substitute in x plus 2. That moves the graph 2 to the right. Square root of x just moved 2 to the right. And lastly, you can see that x minus 2 is plugged in here and here. So I'm going to take x minus 2 and plug it into the original. So that would be an x and that would be an x. So we'd have x squared minus 4x and the plus 5. All right. Now, if you get more dynamic or complicated functions, there's more than one correct way of decomposing them, right? So we can actually do it. This says 2 ways, but there are actually 3 ways of writing f of x and g of x. See how many you can come up with. So I'm just going to write f of x equals and g of x equals for each one. And then you see just how many you can come up with on your own. See if you can get all 3. If not, just try to get 2. So the first one, we have a square root, so it might be look at that parent function and say, okay, square root of x, and I'm just going to plug in 3x squared plus 1 into there, right? And that'll give us the square root of 3x squared plus 1. That's probably the most straightforward if you use the method we did earlier. The other 2, however, got to do a little more than that. Anybody come up with any ideas? Throw it out there. Of x plus 1, okay, which makes g of x 3x squared. Perfect. So if I plug 3x squared in for x, I do get 3x squared plus 1 and square root. Anybody get the last one? Two? Of 3x x squared plus 1/3. All right, so if I plug that into there, you get 3x squared and you get plus 1 with a square root. Very good. That's the first time I've seen that one. Good job. There are. I haven't seen that one before. Yeah, the other way I was thinking was square root of 3x plus 1, and then the g of x would just be x squared. Yeah, this has much more flair. So, fair. You get a star for the day. All right. Good job. All right. Lastly, so why is this important? It mentions at the very beginning, also right here, it's to combine different formulas together. So something more real world here. This is the kind of stuff that shows up on the FRQs where you have to explain things. The first 2 explain the meaning. Those are just from Algebra 1 with basic function notation. All you need to know is the units of each of the numbers, and you can write the justification or the reason. So read this. So Jim plants wheat in his farm in Kansas. The function w of a, the whole function gives the amount of wheat in bushels. So our 275 here is 275 bushels that he expects to harvest if he plants the wheat on a acres, 8 amount of land. Right? So this 5 stands for 5 acres. 5 acres will yield 275 bushels. So we can say something like that. Jim plants 5 acres. Wheat. And yields, or produces, however you want to say that, produces 275 bushels. And then next we have what is the meaning of M of 65 is 550. So we look at the units of both of those. So when the wheat is harvested, Jim can calculate the amount of money M in dollars. So we have M is going to be dollars, so 550 is going to be $550 that he'll earn from selling W bushels of wheat. Yep. So the 65, right? Jim sells 65 bushels for $550. So we had to take the, like you can take an answer from the first one and then plug into the second. If I want to know the acreage and how much money that produces, that's what the composition will do. So right here it says W of 4, meaning find how many bushels you get from 4 acres and automatically plug that into the money formula and see how many of those bushels will give you how much money. So just take the first part of part A. Jim plants, this time it's 4 acres of wheat and sells it for $2,100. So it completely bypasses how many bushels you have. So if your goal is just to find out, well, I have this much acreage, how much money does that get me? It gets you directly there by just combining the two formulas into one. And if we actually had the expressions for the formulas, we could start plugging it in and getting the actual number and see how the 2100 is actually calculated. Okay. So there we go. That is our composition of functions.